independence, the basis linear independence, plus we will discuss about the spanning and linear combinations. So basically, in this session, we will describe about the vectors inside the structure of a vector spaces, that how the kind of vector spaces are inside of that one. So the important definition is starting from here. The first definition is about the linearly independent vectors. So suppose that S is a set of vectors in a vector space V. S is any set containing like V1, V2 up to VR. These are the vectors. And we say that these vectors are said to be linearly independent if we take K1 V1 plus K2 V2 plus up to so on KR VR equal to 0, like equal to 0 vector, implies that K1 equal to 0, K2 equal to 0, up to Kr equal to 0. Like these constants are equal, must be equal to 0. So it means for this type of homogeneous system, we always get a unique solution or a trivial solution which is 0, 0, 0. If this is happening, then we say that such a system is a such a vectors v1, v2 up to v are linearly independent vectors, and this set S is a linearly independent set. And on the other hand, if we do not get the all values k1, k2 as a 0, then we call such a set as a linearly dependent set. So this is basically the relations of that vector. For instance, one of the easy example is for that one is like if we take E1 in since we know that Rn is a vector space and we take a unit vectors. These are standard unit vectors. E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0 up to other all are zeros, and up to En is 0, 0, 0, 1. If we take these choice, then particularly if we take in R3 I as is 100, J as 010, and K as 001. And if we take its linear combination as a K1I plus K2J plus K3 K is equal to 0, then we will get its trivial solution like K1, K2, K3, all these are the zeros. All linearly independent vectors. And but since you know that we are always not taking the vectors which are the very easy like 100, 010, 010, what happened if we have the different form of a vectors? For instance, if we have v1 is equal to 1 minus 1, v3 is the 3 2 and 1. Now let us check that is the vector these are linearly independent or linearly dependent. So for this, let us take it's a linear combination as a k1 v1 plus k2 v2 plus k3 v3, where v1 v2 v3s are given and k1 k2 k3s are scalars. So these are unknown scalars and we need to identify the values of k1 k2 and k3. If the value of k1 k2 k3s are only the 0 0 0, k1 is 0, k2 is 0, and k3 is 0 only, then we conclude that these vectors are independent from each other. And if the value of k1 or k2 or k3 is other than 0, mean anything else, or since it's a homogeneous system, then its values can be a parametric value. Then we conclude that these vectors v1, v2, v3s are linearly dependent. Now look, if we put k1 v1 plus k2 v2 plus k3 v3 equal to 0 vector, 0 vector in R3 is 0 0 0. Now it will gives us k1 multiply with all these three values, k2 multiply with all these three, 5 6 minus 1, and k3 multiply with the 3 2 1. And we can add vectors, and we know that we can write as a single the form. But the first all handles are zeros. Let's say becomes a we need to figure out the values of k1, k2, k3 by any value, any method of a linear algebra. We can apply elimination method or Gaussian elimination, or we can apply the elementary equations, or we can use Cramer's rule, whatever the method we want to apply, we can use it. And we need to figure out the values of K1, K2, K3. Now, in this example, if we get the values of a K1, K2, K3, then it will give us a parametric solution. For instance, K1 is minus 1 by 2t, K2 is equal to minus 1 by 2t, and K3 is equal to the t, where t is a parameter. So it means the t is not only the 0, but t can be changed as a 1, 2, 3, up to so on. So it means the value of K1, K2, K3 is not equal to 0 only. Hence, we conclude that the vector V1, V2, V3 are linearly dependent, not independent. So this is the way and criteria to check the linearly dependency and independency. Similarly, in R4, but this is important and good example. Look, in R4 instead of 4, we have 3 vectors. Again, we need to check that either these three are linearly independent or not. So what we need to do is that we just write as a linear combination K1 V1 plus K2 V2 plus K3 V3 equal to 0, and then put the values of a V1 V2 V3 over here. Then it will give us K1 plus 2K 4K2 plus 5K3 is equal to the first value of a vector, which is 0. Secondly, 2K1 plus 9K2 plus 8K3 is equal to again the 0 on the right hand side, and this gives second equation. And third equation, like 2 times K1 plus 9 times K2 plus the 9 times K3 is equal to the third value, which is 0. So it will give third equation. Similarly, the minus K1 minus 4K2 minus 5K3 is equal to the 0. So look, we will get the 4 equations from these 3 variables. And it's again a linear system. We can apply elementary row operation or any method to solve this homogeneous system. If we get a trivial solution means only the 0, 0 solution of this homogeneous system, then it means this system is a this V1, V2, V3s are a linearly independent vector. As we see that the only 0 is the solution of this system. So it means these all vectors are linearly independent to each other. The next example is also the important in case we are playing with the polynomials. And in the polynomials, we have a vectors like 1x, x square up to xn. Every polynomial can be generated with these one. So 1x, x square up to xn, these are linearly independent in Pn, because Pn, a polynomial of degree n, is generated by these vectors. When we write as a linear combination of that one, so it just need to be put the constant like a naught p1 plus a1 p1 plus a2 p2 plus up to so on a n p n equal to 0. If we take this, then on the right hand side we have only the 0. It means the a naught is 0, a1 is 0, a2 is 0. So it means all the coefficients are only the 0. And that's why we conclude that the vectors in Pn like 1, x, x square up to xn, these are linearly independent to each other. And in case of different polynomials in P2, suppose we have three vectors in P2 or three polynomials in P2, like polynomial of degree 2. Then, like for example, P1 is 1 minus x, P2 is 5 plus 3x minus 2x square, and P3 is 1 plus 3x minus x square. So need to check that all these are independent to each other or not. So independency means that is this possibility that if we add P1 and P2, we get P3, or if we multiply something with P2 and multiply something with P3, we can get P4. So this is the independency of something like any of the vector will based on the Hello, students, can you hear me?
Now we can.
Okay, okay, there's some interruption in the internet. So, okay, so I'm saying that independency means that all these three vectors are independent from each other or not. For example, is this possibility that if we multiply some k1 with p1 and some uh, k2 with p2, and if we add or subtract, then we will get the third of the polynomial. So, if this is so or not, or all the threes are independent from each other. So for independency, we can apply this simple take its linear combination equal to the zero, like k1 p1 plus k2 p2 plus k3 p3 equal to the zero, and plug these values over here. Now, when we arrange them with the constants, like uh, 1 is constant, 5 is constant, and 1 is constant, so it will give us just make constant one side, take xx elements and its coefficients on the other side, and x square with its coefficients on the other side. And on the right hand side, as we have only 0, it means the right hand side is 0 plus 0x plus 0x square. So if we compare the first with the first, we consider the second with the second, and we consider third with the third, it will give us the first equal to 0, second coefficient is equal to 0, and third coefficient is equal to 0. And hence we will get these three equations. And our objective is to solve these three equations by employing the elementary row operation. And we know that we can solve any linear system by elementary row operation or any method of that one. So if we figure out the values of k1, k2, k3, here it is mentioning over here that these are linearly dependent. For example, the values of k1, k2, k3s are not only the zero, but there are any other values of a k1, k2, k3 as well. So hence it means that the P1, P2, P3s are not linearly independent. They can be depend to each other. For example, this it can be the chance that the P2 can generate P3, or P2 plus P3 can generate P1, or if you subtract P1 and P2, we will get P3. So it's mean they are interrelated to each other because they are dependent. So here also there is some criteria. A set S with two or more vector is linearly dependent if and only if at least one of the vector of S is expressible as a linear combination of the other set of S. Yes. So for example, if they are non-zero, then one can if the value of k is non-zero, then we can write this element, the all other elements on the other side, and k can be divided from the other. So it means p1 can be write as a linear combination of the other of that one. So this is the some result regarding that. Similarly, the the two or more vectors are no vector of if and only if is expressible as a linear combination of each other of other in vectors set S. For instance, if they are linearly independent, then the only k1 equal to 0, k2, all the k1, k2, k3s are 0. And if you take the elements on the other side, then we cannot express the p1 as a linear combination of the p2 and p3. Similarly, p2 cannot be expressed as a linear combination of p1 and p3. And similarly, the p3 cannot be write as a linear combination of p1 and p2. So this topic is actually interesting, but you need to be put some attention of that one is because here yes, this is the example. If the vectors v1, v2, v3 are not independent, like they are linearly dependent, then we can express its values like 1 by 2 v1 plus 1 by 2 v2 minus v3 equal to 0. This is the linear combination. And you know k1 is 1 by 2, k2 is 1 by 2, and k3 is minus 1, for which this is equal to the 0. It means k1, k2, k3 are not 0. The k1 is 1 by 2, k2 is also 1 by 2, and k3 is minus 1. And we can write v3 as a 1 by 2 V1 plus 1 by 2 V2. It means V1 is a linear, V3 can be write as a linear combination of V1 plus V2. This is the express as a linear combination of the others. Now, a set that contains 0 is always linearly dependent. So this is very important that if you have some sort of a sets, and if there is any zero vector on that one, any one of that, then this collection must be linearly dependent, not independent. And if this is linearly dependent, then a set exactly one vector is linearly independent if and only if the vector is not zero. Like if you have only one single vector other than zero, then such a single vector is always linearly independent because it's alone, and alone is always independent. And a set that a set exactly two vectors is linearly independent if and only if neither vector is a scalar multiplier of each other. Yes, if we cannot express the one vector as the linear combination of others, then that two vectors or more are linearly independent. Here are these are examples of two functions like x and sin x. We can also check that all these vectors are independent or not from each other. So, like if they are dependent, then it means v1 and v2 are on the same, are collinear or on the same of the form. Similarly, the v1 and v2s, these are collinear. These are straight and these are coming on the same line. But V1 and V2 over here in the third figure, you can see that these are independent and these are not related to each other. Yes, these are some examples for that one is, and this is one result in that direction that if S is a set, V1, V2 up to VR be the set of vectors in Rn. If R is strictly greater than 0, then S is linearly dependent. Yes. For example, in we know the basis, the dimension or the number of element in Rn are n, and if we take more vectors than n, then that combination will be always linearly dependent because look in if R2 we know that the basis of R2 is 2. So the basis of R2 is based on the two vectors only. Like there are the only two vectors in that are sufficient to generate the whole space. So if we take the third vector, then it means the third vector can be write as a linear combination of the other two vectors. So it means that these are linearly dependent. So there is also the one criteria for checking the functions that or the following vector the functions are linearly dependent or independent. So for that, so we can create a metric form of that and apply its derivative test. And if we take its derivative and then apply its determinant, and if the determinant is non-zero, then we conclude that such a vectors are independent. And if the determinant is zero, then it means these are linearly dependent. So this is also the criteria for checking the linear dependency or independency of the vector. And so these are some examples of applying this Wronskian matrix determinant to check that the given functions are linearly dependent or independent. So these are the related topics for that one. And beside here, if we describe some notes and share to you some details, we describe first of all about the linear combination. So what is the linear combination? Like suppose we have a vector space V and V1, V2 up to VR be the vectors in V. So a linear combination of these vector is any expression of the form W is equal to K1 V1 plus K2 V2 plus up to so on KR VR, where K1, K2, KAR are the coefficients, or we are also called it scalars, like they are always a real numbers. and the vector W is known as a linear combination of vectors v1, v2 up to vr. So this is called the linear combination. And for example, as we have a vector v is equal to minus 7, 6, and we can let us see that is this possible that we can be right as a linear combination of the vector v1 and v2, as uh, v can be right as a 2 times v1 minus v1 and v2. And remember that 0 is the vector, is a this 0 vector is always a linear combination of v1 and v2. Every 0 vector can be write as a 0 uh, v1 plus 0 v2. And it is easy to see that 0 vector of any vector of the form of v1, v2. Now, now the vector v3, vector 3, 2, minus 1. Let us take this one vector 3 to 1 can be write as 3 times 100 plus 2 times 010 plus minus 1 times 001. It means this vector 3, 2, minus 1 is the linear combination, can be write as a linear combination of 100, 010, and 001. Now, the next thing is about the spanning. Spanning is also the important thing, like a set of all linear combinations of a collection of vector v1, v2 up to vr form a vector v is called spanning of v1, v2 up to vr. So it means that the all possible collection of all possible linear combination is called the spanning. V1, v2 up to vr is always a subspace of v because with its linear combination we can generate several new vectors. That vectors generate the entire space. Then we can write as v1, v2 up to vn, and this v is said to be the span by v1, v2 up to vr. Now, the and the all vectors of R2. Like if we want to generate any vector A, B, it means like for example, if we want to generate 1, 2, then here in place we put A as a 1 and B as a 2 over here. So it means that 2 can be generated with V1 and V2. So it means that R2 is spanned by generate by given vector that a collection of all vectors V1, V2, VR form a vector is said to be independent if we take its linear 0 AR is not 0, then we conclude that such a vectors are linearly dependent. Now, here we can see that the vectors, you can see that if we add first vector and second vector, then it will gives you third vector. I mean, like first vector plus second vector is the sum of vectors is equal to the third vector. It means these three vectors are not independent to each other. Similarly, if we take any linear combination of these vectors, so they are always uh, and the second vector, then it means these vectors are linearly dependent. And another example is that if we have a vector v1 and the other vector is kv2 are linearly independent for every values of k. For example, if we have a v is equal to v1 is equal to 1 0 and v2 is 2 0, then one can see that v2 is equal to the 2 times v1. It means k v1 and v2 are not independent to each other. And another thing is that if in Rn we have the vectors v1, v2 up to vr, these are linearly dependent vectors. If these are linearly dependent vectors, then if we take its determinant by v1, v2 up to vn, then its determinant must be equal to the zero. For example, look over here in the example that if we have the vector 1, 1, 0, 0 minus 1, 2, and 1, 0, 2. Determine whether these vectors are linearly dependent or independent. So as these are three vectors of R3, so we just need to take its determinant. And if we take its determinant, we saw that the answer is 0. So it means these three vectors are linearly dependent. This is also another nice criteria or simple criteria to check that what happened with the vectors when we take its determinant. If determinant is 0, then it means that these vectors are linearly dependent to each other. And if the determinant is 0, it means these vectors are linearly independent. And it means also that the values of k1, k2 up to k3, all these values are only the 0 and only the trivial values. Any question you want to ask on this topic? If you have any question, then you can ask. Students, can you hear me?
Yes, so instead of using the raw echelon form to prove that this is a linearly independent, can we just use the this one that you just wrote, the determinant part on the assignment? Is it fine for you?
Oh, yes, but one thing, there is a one question arising. Look, if instead of three vectors, here only the two vectors, then how you can check it that how you can apply the determinant? Determinant we can only apply when the number of vectors are equal to its dimension. Like here in we have in R3, so there are three vectors. Here in you can see that there is a result like if we have the R vectors and R vectors of R v is equal to v R power n sorry R power small r, which it's like the number of elements are the same three as there are the three, but instead of there if there are four or two, then we cannot apply that. But one thing I can tell you that if in R3 there are four vectors, then they must be linearly dependent because four vectors cannot be independent to each other in R3. Understand? Or five vectors cannot be independent. If they are three, then there is a possibility that they can be dependent or independent. And if there are the two vectors, not the three in the question, then you can not apply this test. Just apply that the number of vectors are same as the number of a dimension. Like dimension is three, so need to be checked for three. So this is the important case for that is. And Now, if we see some examples, some like problems from the assignments, so express U1, like we have a question that express the uh, linear combination as a U, V, and W. These are available. So just you need to take K1 U1 plus K2 U V2, sorry, K1 U plus K2 V plus K3 W is equal to 616, and then solve that system for the value of a K1, K2, K3. If you get the value of a K1, K2, K3, then just write uh, as a K1, the value of K1, then U plus the value of K2 with V plus the value of K3 with W is equal to 616. And the other one is very simple or easy, like you can write as a 0 times, if you find the value of a K1, K2, K3, which is equal to the 000, like K1U plus K2V plus K3W is equal to 000, then you can only find 0U plus 0V plus 0W is equal to 000. It means that uh, the 000 is only the solution or only gives us a linear combination with this vector 000. Similarly, for the third part, you need to take K1 or just say C1 U plus C2 V plus C3 W is equal to 789, and then solve the system. And definitely you can get some values. If you are unable to find the values of a K1, K2, K3, it means that 789 cannot be right as a linear combination of the U, V, and W. And here, look, in R4, need to check that which of the following sets are linearly independent. If they are four, then you can apply the determinant method. But if there are three, how you can apply it? So for this, you just need to take K1 first vector plus K2 second vector plus K3 third vector is equal to 0, 0, 0, 0. The zero vector of R4 on the right hand side, and then find out the values of a K1, K2, K3. And if the value of K1, K2, K3 is only the zero, then it means such a system have a the three vectors are linearly independent. And if the values of a k1, k2, k3 are the parametric or based on t, then we conclude that such a
Sir,
the vectors are linearly dependent. And in the next problem,
sir,
determine whether, yes, please.
I don't think I can see the screen. I don't know if it's only me or what.
Students, can you see the screen now?
Yes, we can see the screen, sir.
Yes, we can
Okay,
see the screen.
okay. So I think there is no problem, but I will also share the recording, and I hope you can see the screen at that time. But please check on your hand.
All right, thanks, sir. Let me get out and get in.
Okay. So in the problem number 12, determine whether the solution space. Solution space mean remember that solution space of a homogeneous system is always a vector space, and determine whether this homogeneous solution of this system is ax equal to 0 is a line through the origin, like it's a parametric solution, or a plane through the origin, again that kind, or the origin only. Origin only mean only the 000, like the 00 solution. So determine whether. So for this, again you solve here for K1, K2, K3, and determine whether the solution space Ax equal to 0. So just need to solve here for K1, K2, K3, and then check the what are the values of a K1, K2, K3. If the values of K1, K2, K3 are only the 000, then it means we conclude that uh, if the values of a K1, K2, K3s are only the 000, then it means that the solution space is aligned, or the solution space is only the origin, because 000 is only the origin. And if the solution is the parametric, like k, it's k1 equal to some form of t, K2 and K3 are also based on some parameter T, then we conclude that these are the line or plane through the origin. So this is the problem for this one. So again, I tell you that if the number of vectors are more than in R4, if the vectors are more than the dimension like 4, then they will always be linearly dependent. And this there are two things. One is linear combination and one is the linearly independency. And the base of both, there is a there are two things others. One is the basis. Like is the following set is a basis of some vector space or not? And the second thing is that what is the dimension of any vector space? So the linear combination and linearly independency give us about the idea about the basis and dimensions. So that we will discuss in the next session. But I hope when you will study this topic, you will see that what is the linearly independency, like all the vectors are independent to each other or not in some certain finite group. Like if we take some vectors and apply this as a linear combination equal to 0, if the values of k1, k2, k3 is only the zero solution, then we conclude that v1, v2 up to v are linearly independent vectors, and this set is a linearly independent set because its elements are independent from each other. And the other was a linear combination. I hope you remember that the linear combination is just take as a linear combination of the form of that one. If you can get the value, some particular values, like the question arises that is this vector can be write as a linear combination of the other one or not? So the simple criteria is just take this vector is equal to k1 first vector plus k2 second vector plus k3 second vector, and then solve this one for the values of a k1, k2, k3. If you get the values of a k1, k2, k3, then it means the given vector can be expressed as a linear combination of the vectors like v1, v2, and v3. If you cannot find the, if you solve the system but there is a no solution for k1, k2, k3, it means that this given vector cannot be write as a linear combination of a the
Yes,
vector
man.
v1,
What?
v2, v3. Now, if you have any question from this topic, you can ask your question.
Yes, sir.
Yes, please.
So I heard you saying when we are finding the vectors, if in R4, for instance, and they gave you three vectors in R4, then we have to introduce the fourth vector, which is 0, 0, 0, so that we can use. Yeah.
Uh, there's some.
Can you hear me, sir? I don't know
Yes, I
which
can
one
hear
is
you.
that.
Yes, please. Can you repeat your question? Yes.
Yes, I heard you saying if they give you a space in R4 space, and then they ask you to determine if three vectors in that R4 space are linearly independent or dependent, then we must introduce the fourth vector 0, 0, 0 if we want to use the Wronskian
No, no,
determinant.
no. Remember. Yeah, this is a very good question. But let me tell you. First, I will tell you the zero. If there is any zero vector, if you put over here, then it must becomes linearly dependent. Because if I have this vector, so if I multiply with the zero, like 0 times 4 minus 2 1 4 and 1, then 0 multiplied by any vector is a zero vector. So they directly becomes linearly dependent vector. So zero we cannot change, not take. And another question which you are saying that if we have a three vectors, we need to introduce any other vector. So this is not allowed. If we have a three vectors and we need to check that, determine whether the given these three vectors are linearly independent or not. So it means we only need to check these three vectors. We cannot apply any other vector or zero vector. If there is a, and one thing, look, if I have some vectors and there is a zero vector also in that. Suppose the second vector is 0 or first vector is 0, then blindly you can say that these are linearly dependent, because when you apply apply the element the method that just take as a linear combination equal to 0, then you will never get k1 equal to 0, k2 equal to 0, and k3 equal to 0. It means it have also some other solution. So the question is here, like, let me ask you one question, that if I have a two vector only in R4, suppose remove the third one. My first vector is 1, 2, -2, and 1. My second vector is 2, 4, like 2, 4, -4, and 2. It means if I just multiply first vector with the 2, then it will become the second vector. Then it means this vector is a linearly dependent, because in case if I multiply the first vector with the 2, then we will get the second vector. It means first vector is dependent on second vector, and second vector is also dependent with the first vector. Because if a second vector we multiply with 1 by 2, we will get first vector. This is just I'm saying example. But for the case we cannot know about that, like either they are dependent or independent to each other. So we just take k1 first vector plus k2 second vector plus k3 third vector is equal to the 0, 0, 0, 0, and then solve it for the values of a k1, k2, k3, and k4. If the value of k1, k2, k3, k4 is only the 0, 0, 0, 0, mean trivial solution, then we conclude that these given vectors are linearly independent. And if they are all not zeros, then we conclude that these vectors are linearly dependent. And this is also the simple thing. For example, here if you have four vectors, it can be possibility it might have that if I multiply first vector with the 4 and subtract the second vector, then it will give us a third vector. Or if I add first and second vector, then it will give us four vector. Or it can be possibility that the 2 multiply by first vector and like 3 multiply with the second vector gives you the fourth vector, or vice versa. So it means if this is happening, then it means these vectors or this collection is linearly dependent to each other. So for this, we need to apply, the best thing is that we need to apply k1 v1 plus k2 v2 plus k3 v3 plus k4 v4 is equal to the zero vector, which is 0, 0, 0, 0, and then solve it for the values of a k1, k2, k3, k4. And another thing that I told you, that if you have more vectors, like in R4, we know that in R4 we have the four vectors at least. If we take the fifth vector, then they must be linearly dependent. They cannot be independent, because if there are five vectors, then it means there are four vectors are sufficient to generate entire space. Then fifth vector, if we include the fifth vector over there, then it must be linearly dependent. I hope
So,
you understand this one. Yes, please.
so in the last example where we have five vectors in R4, we're still
Yes.
gonna have K1, K2, K3, and K4. We're not gonna have K5, are we?
Yes, we have. Look, one thing inside the thing is that if we have five vector or six vector, then one thing by default it will becomes linearly dependent. And if you put k1 first vector plus k2 second vector plus k3 plus k4 plus k5, then remember that the k1, k2, k3, k4, and k5 will never have only the zero solution. They must have parametric solutions, because you know how many equations you have, the five equations, and sorry, you have four equations but five variables. Four equations and five variables. So they must, if there are the more variables than equations, then is this have a unique solution or the parametric solution?
Infinitely many solutions,
Infinitely many
parametric.
solutions. Good. So if infinity many solutions, then it means it not have a zero solution. Then it will always becomes linearly dependent. Okay.
Prof,
Remember that if only 0, 0, 0, it means finite solution, like zero solution. But if infinitely many solutions of the k1, k2, k3, k4, and k5, then it means they are linearly dependent. So therefore, if the number of variables are more, then the R4 or 5, like there are 5 or 6 or 7, if you take, then they must be linearly dependent. Yes. Okay. Any other question?
Prof,
Yes, please.
do I understand you to be saying that we only use a determinant to check the linear dependency or independence only when you are dealing with the square matrix?
Exactly, exactly. Yes. When square metric we deals, then it means we can apply the Cramer's rule or we can apply the theory of that one. So in that case, you can apply the determinant and determine. Yes. So determinant we can only apply when we have the number of vectors are equal to the dimension. Like since these are the power, we call its dimension. Although we not studied yet the dimension we will study in the next session, which is there is a full topic on a basis and dimension. Then we will see that what is actually the dimension of a vector space. This is very important thing, that we know what is exactly the dimension. So, but only remember that in R3, if there are three vectors, then we can apply the determinant. Like because determinant is always possible for square metric. So this is the short technique for a square metric only. And if we are dealing with the functions, then we can take the Roskin determinant. So that is the determinant for a function. Just take its derivative and take the particular class, and then we can apply this determinant, and then we decide. For instance, if we have these functions, and this is based on a 2 e power 3x, which is not equal to the 0, and we conclude that f1 and f2s are linearly dependent set. So these are the examples for some class of functions to check that either they are determinate and indeterminate. So here basically we are dealing with the class of a vectors, like vectors of R square, R cube, the class of a matrices. For the matrices, we are playing with the same, but the matrices dimension will be increased. Like if 2 cross 2 matrix, then it means there are 4 vectors required or 4 matrices required to generate that one. And for the polynomials, we need the x square, x cube, like this one. As we describe here, there's a one good example we already saw here uh, to check the independency or dependency of the yes. So this is the example, and also like it means that uh, are these three polynomials are independent to each other or not? Or it this possibility that if we subtract first one, if we multiply with the 4 with the first polynomial and subtract with the second one, then is this possible to get the P3? Or maybe if we make a difference or something with P2 and P3, just add or subtract with some scalar multiple, will we get P1 or not? So if P1, P2, and P3 are independent, then just then the values of its combination will give us K1, K2, and K3 only the 0. So this is actually the criteria and the method which we are using to check the linearly independency. Any other question from your side? Yes, if there is any question, then please you can ask your question.
Sir, can you please explain the last problem in the assignment again? Or is there an example like that in the book, sir, in our textbook?
Yes, I think there is an example in the textbook based on that one, like determine whether the solution space of homogeneous is a. Just I can tell you one thing. You need to take a x is equal to 0. Just I'm putting the hint for you over here. Like just you need to take the uh, take ax is equal to 0. This 0 I make a bold because this 0 is a vector of 3 cross 3. And find the values of x. And remember that this x is like a x1, x2, and x3. Okay, can you solve the homogeneous system? Like, listen, here you have a. So just put ax equal to 0 and solve it for the values of x1, x2, x3. Okay, so this is the simple case, like,
Understood. Yeah.
yes. So for the more, like, I just tell to you how to do this. Like, for the more simplicity, I just make a proper section for you over here. Like, you have a metric A, which is something like that. If like 1, 2, whatever the entries are. For instance, here 1, 2, -6. Okay, and the rest of entries you know. And here, what is x? X is the x1, x2, x3, and equal to the 0. As I told you, the 0 is only the 0, 0, 0, this one. And solve it for the values of x1, x2, and x3. Now, when you solve homogeneous system, then then
Can we use Cramer's rule there, sir?
yes, you can apply any, but it's better you need to use the, it will gives you the simple method. Like, for example, if you use elementary row operation, okay, then it will work. You can, but this is a linear system, you can solve any method. But if you take, then if you get its solution, that one possibility is that your x1, x2, x3 is equal to 0, 0, 0. Tell me, is this possible or not, that the first this have a zero solution? The answer is, let me tell you, if you solve the homogeneous system, then there are only two possibility about the solution. Either solution is a trivial solution, 0, 0, 0, like, because all the things is 0, and when you multiply with that, the answer is 0. And the second thing is that it has a parametric solution. If you get this one, or if I think the proper word is either you get this one, or you get parametric solution. Here I am not writing the solution, but just telling you that solution will be like something like this. Like, just say x1, x2, x3. For instance, these are something like that. 2 times t, maybe here minus t, and here can t, for t belongs to the t belongs to the set of real numbers. Like, here t belongs to the R. This is a parameter. So there are only the two possibilities when you solve the linear system. If you get the first solution, like x1, x2, x3 equal to 0, 0, 0, it means that your solution space is passing through the origin only. And if you get this kind of a parametric solution, then it means that it's a plane through the origin. Like, plane through the origin mean, if you put t equal to 0, 0, then it will also become 0, but it's cover all the other factors. And it's a the other thing is, it's a line through the origin. Line means it have a some sort of a straight line. So these are the possibilities, either of that one. So you need to determine that either it have a zero solution or a parametric solution. From that, you can conclude the answer from this. I hope it's clear. You just take ax equal to 0 and then find out the values of a k1, find the values of a x1, x2, x3. If x1, x2, x3 is the origin only, then it means it has the origin. And if it's not, then we conclude that it's a plane through the origin. And also is a line through the origin. It can be possible that f a1, like, the elements are depending to each others. So, but remember that the line through the origin and the plane through the origin actually coincides here. Like, both have the sort of meanings. but it means you only need to check that either it's plane through the origin or a origin only, like 0 0 solution only.
Understood, Professor. Thank you.
Yes, please.
Oh no, I'm quite not lost, but I'm not finding balance between what is the condition for it to be the line through the origin, and then for it to be the plane through the origin. What is the difference between them?
Line through the origin mean, for example, you have a some sort of equations like y equal to x. If you take y equal to x is a line through the origin, and plane through the origin mean x, y, z's. These are the values. The plane, like in the plane, we have covered along x, y, z, all the three axes. But this is some sort of a another kind of solution. Let me tell you, like if you have a, this is also the possibility like x1, x2, and x3. So if like this is the, say something s, like here I've like your 2t, the second parameter is 4 times s, and the third one is like let me just write t plus something like this. So for s comma t belongs to the R. So because there are three equations, so it might be possible that you have this form of a solution where first is on the based on the t, second is based on s, and the x1 is like t plus s, some this kind of a solution. Then it means it's cover entire the plane.
You are
Okay.
very clear, Prof. Thank you very much.
Because like it can be possible like your when you apply elementary row equations, your these two rows are will become 0 0 0. It means only based on the first equation. Then is in that scenario you will get a parametric solution as well as which is the based on the plane through the origin. It's still it's a plane through the origin, because if you put s equal to 0, t equal to 0, then you will get what, the 0 0 vector. Is there any other question?
Not from my side.
Okay, if there is no question, then we can stop the session because I have another meeting now. Okay, have a good day and best wishes. Okay,
Thank
goodbye.
you, Professor. Bye bye.
Okay,
Thank you,
thank
sir.
you. Bye.